Okay, welcome back to note set number 15. So I'll put a B here. This is part B. So we'll pick up where we left off last time. If you remember, we had established some ideas that link a bandpass signal to components called the I and Q signals, which the I is the real part of the equivalent low-pass signal, and the Q is the imaginary part of the equivalent low-pass signal. And so basically, the equivalent low-pass signal is complex valued version, basically of one spectral side, the positive frequency side of the signal, shifted down to be pretty close to at DC. It's usually straddles DC, but not necessarily in any kind of symmetric way. And so we were able to show that, first of all bandpass signals can be expressed mathematically this way. So what that means is you can create any bandpass signal by simply starting with a cosine at a particular carrier and manipulating the amplitude. And remember, A of t must be greater than or equal to 0. So you manipulate the amplitude and you manipulate the phase as functions of time, and you can create any bandpass signal that you want. Now, just in passing, this constraint that A of t be greater than or equal to 0 can be violated to some extent, but remember that as soon as you start flipping the sign on A of t, what you're really doing is flipping your phase by plus or minus pi, since plus or minus pi corresponds to -1 on the complex plane. So we could allow A of t to be negative as well as positive, but we don't lose anything by constraining it to be greater than or equal to 0. And when we constrain it to be greater than or equal to 0, then it's linked to something that comes from applying the formula that's a real part squared plus an imaginary part squared, and then take the square root of it. So A of t then really does play the role of the magnitude of a complex number. Okay, so that's what we saw last time, and what we want to talk about now is how to actually create these. And first we'll talk about how to create these components in an analog fashion, which is still done in some systems, but there are also digital ways to compute these. And the reason that we want to generate these I and Q components is that when you're doing radar and communication signal processing, it's actually the equivalent low-pass signal, or equivalently the I and Q components, that you're actually working on, or equivalently the amplitude A and the phase theta. So in all of these systems, we want to find ways we get a bandpass signal coming through an antenna. We want to be able to come up with a way of generating the I and Q signals. And then from the I and Q components, we can compute the A of t and the theta of t if we want that. So given a bandpass signal, these are the I and Q components, and we would like to be able to, from x of t, compute these two signals. So we get a clue by looking at this. We've got cosine, so we can play around with trig identities to try to extract these things. So we're putting a 2 out in front. You'll see why as a convenience to make sure we get the right amplitudes. But basically, we're taking x of t and multiplying it by a cosine at some frequency f0. Now remember, we talked about how for a bandpass signal f0 is somewhat arbitrary. if we knew what the transmitter's carrier frequency really was, then that frequency might make an obvious choice for F0. But if we get it slightly off from that, it's not a big deal. All the math still works. So we multiply by F0, and we start off with our original signal in this form. Now, if the transmitter was using a slightly different carrier frequency, that then from what we are using as our assumed center frequency here, F0, that offset would just be included as a linear term in the theta of t part. Okay, so we take our assumed form for our bandpass signal, which is shown here. We multiply by a cosine. Just take advantage of a trig identity that says we get the sum and difference of the arguments of the cosines. So this is the difference. So the 2 pi part cancels with this 2 pi part, and we're left with just the theta. And then we get the sum part, and that's why we end up with a 2f0 part. And so what we see here is that we have separated or created one term that is our in phase term, our x sub I term. So we have that right here, but we also have another term, but it is up at 2f0. So remember, f0 is typically something pretty large. It might be like 50 megahertz or way more than that. It could be like 500 megahertz or a gigahertz or 5 gigahertz. So it's large. It's also very large compared to the bandwidth of the overall signal. So this thing sitting up here at 2f0 is going to be very far removed even from the highest frequency that we would expect. So the next step is to just slap a low-pass filter around this, and that will get rid of these two terms and leave us with just the xi of t. And so that's exactly what we do. We can similarly multiply our x of t by a negative sign and find out that we extract the q part plus another term up at 2f0, and that can be filtered out. So here's the structure, and we can actually build analog circuitry to do this. We have an x of t, so that would be coming in through our antenna and probably through an initial bandpass filter to just make sure that we're isolating just the band that we're interested in and eliminating any other adjacent channels or anything like that. Then we take that signal, and these two boxes here are multipliers, and we're going to multiply the signal times 2 cosine 2 pi f0 and minus 2 sine of 2 pi f0. So that gives us that operation of multiplication, and it shifts things down to DC, but also shifts up to 2f0. And then we build a low-pass filter on each of these legs, and so the low-pass filter will pass this one will pass the I component, and this low-pass filter will pass the Q component. So this is just following the mathematics and telling us how to actually build this. So this is pretty straightforward, and you can build all these parts out of standard circuitry. If you talk to an RF engineer, they'll tell you that these things are called RF mixers. You can build an oscillator that will create a cosine at a desired frequency. You can build a phase shift, a 90 degrees phase shift that is designed to give a 90 degrees phase shift right at the frequency of your oscillator. And so that comes out as a perfect sine relative to the cosine. And these two things will be, perfectly in phase, quote unquote, perfectly in phase. to the degree that you can build this to be a perfect 90-degree phase shifter. So when I say perfectly in phase, I mean perfectly in phase as a cosine and a sine are. So perfectly 90 degrees out of phase. You can build these low pass filters pretty nicely. You can build oscillators, and you can build mixers. So obviously, there's lots of effort involved in making sure these things are built well, but all of these things are very doable. And so once we do that, we've got a very nice structure that we can use to generate these low-pass equivalent signal components. And these things are used all the time. They're used in cell phones, they're used in radars, they're used in, Wi-Fi. Sometimes we do it analog, and as we'll see in just a little bit, we can also do this in terms of some digital computation. So here's one way to do it digitally. You can actually buy a chip. Now this chip is probably dated, since I made these notes long ago for another course. And I don't even know if this chip is still available, but and I'm in no means or in no way touting analog devices. I've just given their contact information here because I'm using their information in my notes, so that seemed fair. There are other companies that make these, and I'm sure Analog Devices makes newer things. But basically, if you look at this structure, this looks exactly like what we just saw. The only difference is that for the discrete time version of this, we don't really need a phase shifter. We can numerically generate cosine and negative sine. We can do multiplication, obviously digitally, and then we've got our low pass filters, and they use a particular type of filter called a CIC filter, but then together with an FIR filter. So basically, without getting into this, it's called a cascaded integrator comb filter. We just talked about the comb filters in a previous set of notes. So if you want to track this down and look at what's actually going on inside these individual boxes, you can. But that's basically the idea of what's going on in there. Okay, so very straightforward to generate these things digitally, and there are chips available for doing that, and at today probably even much higher sample rates. So this is operating at 67 megasamples per second. But that was 16 years or so ago when I made these notes. To give you an idea of, going back to the bigger picture here, we've been talking about bandpass signal ideas, analytic signals, low-pass equivalent signals. Now, I say here our case study. This slide is being drawn from some other notes that I used in another course that kind of keyed in on a case study that I used to drive the whole course. So this is just a particular type of receiver used in a kind of a Department of Defense type system. Where we intercept an RF signal and we're interested in detecting the presence of a particular type of signal, estimating things about that signal, classifying the type of transmitter it is, and then maybe sending information about it over a data link. So this could be radar, this could be communications, it could be any one of those things. Let's try to get rid of this stuff here. Why isn't that working? There we go. Okay, had a little technical glitch there. So the bandpass signal model that we've been talking about, we use to model the RF signal that we would receive in radar, communications, and other things like that. Can often also be used to model acoustic signals in sonar. If we're dealing with audio signals, speech signals, other things like that, it's not terribly useful. But most commonplace is for modeling radio frequency signals that are coming in through some sort of antenna. So we use that model right here to think about what's coming into our antenna and going into the RF front end of our system. The next thing that happens is we go into some sort of sampling subsystem, and we'll be talking more about how to do that in just a little bit. And that sampling subsystem might have some analog stuff up at the front end, and then obviously once it does the sampling, we'll go into the digital or discrete time world. And so the bandpass signal model might still be applied here if our RF front end doesn't do the analog conversion to the low pass equivalent signal. So we still might have a bandpass signal there, in which case the sampling subsystem would be responsible for converting digitally into the equivalent low pass signal. Then we get to the low pass equivalent signal, and we use that as a conceptual tool as well as something that we actually process. So as I've been alluding to, if we go through this system here, once we get to certainly to this point, we are pretty much at the low pass equivalent signal stage. We might delay the computation of it until over at this point. But at some point, either in the sampling subsystem or in our digital front end, the digital front end would compute the IQ components using something like that analog devices chip that we just saw. But at some point in this stream, we literally get samples of the I component and the Q component, and that's what we actually do our processing on. So when we process to detect the signal, we're processing IQ. When we're doing estimation, we're doing our estimate processing using the IQ. When we're compressing and sending information to some other sensor to cross-correlate with perhaps, we're dealing with IQ. Now, we might also convert at some point that IQ into envelope and phase. So, for example, when we're doing signal detection or maybe even classification of emitters, we might want to look at the envelope shape and the shape of the phase to see, what kind of pulse shape do we have, what kind of pulse widths do we have, what kind of, do we have like a linear FM modulation on our pulses, things like that. So all of the processing inside our digital signal processing domain is done when we're doing RF processing, is done on the basis of this low pass equivalent signal. So the analytic signal that we talked about is largely just a conceptual tool. So we're thinking about it as just a means to convert, at least conceptually, some continuous time RF band pass signal into the analytic signal, and then as a stepping stone to our ideas for the low pass equivalent signal. I do want to point your attention to on an upcoming slide, maybe even the next one. There is an issue with terminology within MATLAB regarding analytic signal and Hilbert transform, and I'll point that out in just a little bit. So we also talked about the Hilbert transform of a signal, and most of the time we're not particularly interested in the Hilbert transform in and of itself. Again, it's just kind of a step that we take in getting to the equivalent low-pass signal. So I will point out again that there is this issue with some terminology with MATLAB, and I'll clear that up. So here is that MATLAB warning. There is a command in MATLAB called Hilbert, and you would think that if you put a signal X into this command, what comes out is the Hilbert transform. Well, it's not quite true. The first thing you have to be aware of is if you put in something that is complex, it processes only the real part of that. So it's expecting a real valued input, which it makes sense based upon what we've talked about. Now, what you would expect from the name to come out is the Hilbert transform of that real valued signal that went in. But that is not actually what comes out. If you see what that help entry from MATLAB is, it says the real part of the result is the original real data. The imaginary part is the actual Hilbert transform of the real data that went in. So if we look back and see how we defined our analytic signal, the analytic signal is the original signal in the real part plus J times the Hilbert transform. So what they're telling us here is that what Hilbert actually computes is the analytic signal. So just be aware that the Hilbert command doesn't give you the Hilbert transform, it gives you the analytic signal. So if you really want the Hilbert transform, apply the Hilbert command and then extract just the imaginary part, and then you have what you want. All right, I'm not going to spend a lot of time going over this. This just summarizes all the results that we went through in just one nice location, so you can kind of see it and think through all the ideas. So it'd probably be a good idea to print this out and then have it handy next to you as you go back through this set of notes and see how all of these different results came to be. So now a question. Let's go back. Well, I can't easily go back. This recording program, as soon as I go back, it starts saying, things like, do you want to just replace what you already recorded? Remember, we talked about taking our RF signal, putting it into some sort of analog circuitry that generates the I and the Q. So here's our I part, here's our Q part. And we saw what that box would consist of. It would be a splitter, two mixers, an oscillator with a phase shifter to create the 90 degrees phase shift, and two low-pass filters. So we get the I component and the Q component coming out. And if we generate this through an analog circuitry, the next thing we're going to want to do is put an ADC here and put another ADC here. So we're going to want to sample the I part and sample the Q part. And so the question is, what sampling rate should we use? So if we started with an original RF signal that has a bandwidth of B, when we think about what we get for the low-pass equivalent signal, ignoring the fact that we might not have this exactly centered, but let's assume that we end up with it at least approximately centered or reasonably close to being centered. We see that we have a maximum frequency of B over 2, and standard sampling theorem tells us that we should sample at twice that maximum frequency. So our sampling rate would just be B. And what we'll see in just a little bit when we talk about bandpass sampling is that bandpass sampling will tell us that we need to sample this bandpass signal at a rate that is more than 2B. So what's going on here? Seems like we're getting something for fewer samples than we really should. And The reality, here's my just reference to something that we'll talk about in just a little bit, called in the next set of notes, called bandpass sampling, where we'll see that we should do bandpass sampling at a rate bigger than 2B. And here we're saying that we can sample the equivalent low-pass signal at just a rate bigger than B. But here's the issue. Remember, the equivalent low-pass signal is complex valued. So when I take a sample of the I, well, let me say it this way. To sample the equivalent low-pass signal, I need a sample at this instant of I and a sample at this instance of the Q. So I need a sample of each of those, and so I'm actually sampling two signals at a rate of B versus here where I'm sampling one signal at a rate of 2B. So everything does kind of make sense, and we'll see that this makes a little bit more sense once we talk about bandpass sampling in a little bit more detail. All right, the rest of the slides in this note set just give you some examples of I and Q components for a few different cases so that you can kind of see what these things look like. So for a communication signal type known as BPSK, or binary phase shift keying, the information lies in the phase, and the phase just switches from, in this example, pi over 2 to minus pi over 2. So this theta of t looks like this, and at least in an ideal setting, it just flips between two values. That's it. And so if we wanted to send the sequence 1, 0, 1, 1, we could send it like this. And here's a kind of a simplified version of what the actual RF signal of that would look like for a very low carrier frequency compared to the interval for each bit. But you can see that these switches here, the changes in phase, create discontinuities in the RF signal. So that's what this thing looks like, and we would like to try to figure out what are the I and Q components for this particular example. Or equivalently, what is the low-pass equivalent or the equivalent low-pass signal for BPSK? So if we apply our result, we have xi of t is given by this, xq of t is given by this, and for this example, we see that, and I've kind of set this up in a very careful way. If we had a small phase shift, things would change somewhat, but for this very careful setup here, I see that my in-phase term is just 0, and everything boils down to just the quadrature term. And so I see that I'm going, remember this is switching between pi over 2 and minus pi over 2, which makes the sign switch between plus and minus 1, and that's why that's switching between plus a and minus a. So it's very easy to, from the, in this case, just the quadrature term, determine what was the bit pattern that was sent. So I would encourage you to think about what would happen if our original signal had a slight phase offset, so that we weren't switching between plus pi over 2 and minus pi over 2, but just add some small offset to each of those. So let's call that delta. So it'd be plus pi over 2 plus delta and minus pi over 2 plus delta. You should be able to figure out what impact that would have on each of these two components. Let's think about quadrature phase shift keying. Again, we'll keep this simple so that everything is kind of perfect with phase alignments and things like that. In that case, theta of t is just going to jump between 4 values, minus pi over 2, 0, pi over 2, and pi. So we've got this value, this value, this value, and this value. So there's our 4 values. And depending upon which of those 4 values, we have one of 4 possible different bit patterns that can actually arise. So we can see that with this structure, we can send 2 bits for every symbol interval. So that's our theta of t for this particular example. And if we figure out what our in-phase and quadrature terms look like, using these formulas, we find out that we get an xi of t that looks like this, and an xq of t that looks like this. And now we see that both terms are kind of flip-flopping back and forth between 0 plus a and minus a. And if we imagine, this isn't exactly how we determine to decode these or to detect these, but it illuminates this idea. If we think about in the center of each one of these little subintervals, measuring where we are, what the value is for this, we can convert these different possibilities into these 4 different positions on the in-phase axis and the quadrature axis. And so if you've studied digital communications, this is the concept of signal constellation. If you haven't studied that, it's not a big deal. You can still just look at this as an example of what our I and Q look like. But the point is that we're stripping away the impact of the carrier, and we're extracting how the amplitude and phase are embedded, have information embedded in them. Let's look at another example, moving away from communications and into radar processing. So a radar in its simplest form sends out well, maybe not its simplest form, but in A form, sends out a stream of pulses or a train of pulses. And each one of those pulses is on a carrier at a specific frequency. But we've also often impart a certain phase or frequency modulation on that carrier during each pulse. So we know it's an RF signal, so we can represent it as using our standard RF signal, bandpass signal model. And so if we look at that, looking at what's going on inside here, so that omega ct plus theta of t, that is a time-varying phase. It has units of radians, right? Theta is a phase, so it's in radians. Omega sub c is in radians per second, so times the seconds of the t. Omega sub c times t gives us something that is in radians. So that whole quantity is in radians. And if we want to find, well, let me say it this way. And so that is our instantaneous phase. And since frequency is the rate of phase change, right? It's radians per second is our unit for frequency. Just like we have position in meters, and then we have velocity in meters per second. So if we've got a time-changing position, we take the derivative to get the velocity. If we've got a time-changing frequency, or I'm sorry, time-changing phase, we take the derivative to get the instantaneous frequency. So if we take this derivative, it will give us a function that shows us how the frequency changes with time. We still have this carrier frequency that's like a fixed frequency, but the instantaneous frequency will fluctuate around that carrier frequency. So if we take this derivative, let me see if I can get rid of some of this stuff here. So if we take this derivative as indicated, we pass it through this sum here. We're going to take the derivative of that, which will just be omega sub c, and that leaves plus the derivative of theta of t with respect to t. So what we see is that the instantaneous frequency consists of kind of a center frequency plus some deviation around that center frequency. And so one of the modulations that is often put on a pulse in a radar pulse train is called linear FM. And so what we want is for this whole thing to be a line that goes through the center point of omega sub c. So to do that, I'm just showing some arbitrary pulse shape here. Radars aren't necessarily nice, perfect rectangular pulse shapes, so it might have some ramp up and ramp down, which I'm showing here. And then the theta of t, if I draw it here and I draw it as a quadratic, we'll see that taking the derivative of that is just finding the slope of this thing. So right here, the slope is equal to 0. And so the slope function, the derivative, will go through 0. And up in this region, we have a negative slope. And in this region, we have a positive slope. And since it's a quadratic, the derivative of a quadratic is a straight line. And so, yes, indeed, we get exactly what we expect to get here. We get that our instantaneous frequency deviation is a line that at the center of the range goes through 0, so that when I add plus omega sub c, the whole instantaneous frequency in the center will go through omega sub c, and in the early part will be below omega sub c, and in the later part will be above omega sub c, but it will transition from that lowest frequency to the highest frequency in a perfectly linear fashion. So this is exactly what goes on inside a particular class of radars that are using so-called linear FM. So if we look at this, the LPE signal for the radar signal case that we just talked about for linear FM, we can immediately write it out like this. So it's just A of t, and here's our theta of t, and we leave in some uncertain small frequency. So we may not know what the actual carrier frequency is that the radar is transmitting at, but we're going to try to guess and get it pretty close. And suppose we get it close enough so that omega sub L is fairly small, but not so big that it would cause problems. So if we take the derivative of this, we're now going to see a straight line that in the center of its extent goes through this small number, this small offset frequency omega sub L. So if you use that structure, use the equations that we just talked about, and you set up the phase following that quadratic and put in the carrier, small carrier offset, and you compute this in MATLAB, you can actually get a plot of what the I component and Q component look like for a particular given case. So this is just a plot of that. So suppose we intercepted a radar signal and we know that it's a linear FM, and we would like to know something about its modulation rate. So in other words, we'd like to know how rapidly this particular linear FM is sweeping through the frequencies. So that would be its modulation rate, or in other words, the rate of frequency change. So to show how we would do that, we'd have our antenna, which picks up the RF signal. RF front end would amplify that and would also apply a bandpass filter to attenuate and effectively eliminate the other signals that are coming through the antenna but are not our desired signal. So the antenna might be fairly wideband and picks up a bunch of different signals. Then the RF front end, actually one of the very first things would be a bandpass filter that would hopefully narrow us down to just the band that we're interested in, or at least some subband. Then we'd apply some amplification, and eventually we would get down to some circuitry that would compute the I and Q components. And I'm showing it here as analog, but it could just as easily be digital, or meaning a discrete time computation, like with that chip from Analog Devices. But nonetheless, we get our in phase and our quadrature term, and in reality, we would want those as discrete time versions. So if we get this through an analog, we would put in an A to D converter in each of these positions before we do any of the other processing. Then we can find the time varying phase by just doing an arctan computation of the imaginary part over the real part. So that's no surprise. And so at this point we get something that looks like this. And then we just want to take the rate of change of this thing. So if we take a derivative, if we take one derivative, we get the instantaneous frequency. If we take a second derivative, we're getting the slope of that instantaneous frequency. So differentiating twice, actually that term will go away, and we'll get the second derivative of that, which will give us the slope of the linear FM. Now, all of this would probably be done digitally. So that's just one example of how we might use these I and Q components for actually doing real things. Now, suppose you want to simulate this processing, and this is an important issue. Would you really want to simulate the signal that's here or even here? No. Certainly simulating the signal here would require a huge sampling rate to simulate an RF signal actually up at its highest frequency. But we don't need to do that. With these ideas, all we really need to do is simulate the I and Q terms that we're going to get. So these things are, just look like low pass signals that are centered at DC and have, appropriate sampling rates, which are much smaller than the sampling rate would be needed to actually sample the RF signal. So this is a common mistake when I give my graduate students a task of simulating a communication setting or a radar signal or something like that. They almost always try to do it this way if I don't warn them ahead of time, and sometimes I don't, and just let them stumble into it. Then we eventually get to the point where I say, well, really all we need to do is generate the I and Q components, and it'll be much easier. All right, so hopefully this has given you some idea of ideas of bandpass signals and the I and Q components and the envelope and phase, and how some of these ideas are used in actual signal processing. So we'll stop here and we'll pick up in the next set of notes.